Okay, so today we're going to talk about this return-to-libc attack. The idea of the return-to-libc attack, as we said, in the buffer overflow attack. So one of the countermeasures of the buffer overflow attack is to make the stack non-executable. Okay, so you already turned that off, right? When you compile the code, and you actually turn off the non-executable stack. So the stack, so you can tell the compiler, okay, when you compile this program and mark a special bit, okay, in that binary, okay, so and this way the OS will know, okay, when they load this program and they see that bit, non-executable bit, and they will actually mark the stack as non-executable, okay, and this is basically per process, okay, and based on the program that you're running. Because some of the program, they want to run something from the stack. Okay, the OS will allow that. Okay, so this is related. That's why the flag is in the compiler. Okay. Once this actually is turned on, okay, now you have a return address. Okay, and you overflow the return address, right? And now you put the shellcode in here. Okay, you put shellcode in here, and this is not going to work anymore. Right, because as soon as you jump to here, and you're going to find the CPU is going to find out they are executing some code from a region that is not executable. Non-executable actually is a hardware protection. Okay, so you can mark a block of memory as non-executable at hardware level. Okay, so and then the CPU will immediately know that. Okay, and then they will raise a fault and they basically crash the program. So now with this actually turn on, you can't use a shellcode approach anymore, okay? But you need to use some other things. You want to run some other code, okay? So we talked about, so now we cannot do this. But we can still overflow the return address, okay? The goal is to point that to some other code in the memory, not on the stack, okay? So some other places, so let me just draw, okay, some other code in the same memory, okay? Okay, I'm drawing them separately, okay? And so there are a lot of code in the system. And you can jump to those code, and you can execute those code. If you can find the right code, and if you can provide the right argument to those code, you can end up having the same effect. Okay, so we talked about one of the functions we want to is the system function. System function allows us to run any command, right? So, and we know the system function that is in the shared library, libc library. And libc library is already loaded in the memory, okay? Because all the C program relies on the libc, okay? So that library is already loaded, okay? So, and when your program runs, and when you run the system, and basically your code will just jump to that place, okay? And to run that correctly, and you need to provide the command, okay? As we said, we just run the /bin shell. So if we can jump to this, so let's see, we will actually let this jump to this function, okay? And also provide this argument. Now we can end up having this system function execute a shell command, the same result. And this is the code region, okay? Those libc has to be loaded in the executable memory, right? Because otherwise, and no program is going to work, okay? So this is the region is executable, so you don't have that problem, okay? You just need to be able to find that place, provide this parameter. There are three things that we need to deal with, three challenges, okay? Two of them are very simple. The last one is very difficult. So the first one is find where this address is, okay, the address. Okay, we need to jump to that place, we need to find that address, okay? And assuming we are turning off the randomization, okay? We turn off the randomization. So this is the first thing. The second thing is, so how do we find the address of /bin shell string. We need a string, right? We need to provide a string to the system function. So we need the address for that string. System take the address of that string. So we need to get a string in the memory first, and also be able to find the address of that. So we need to have the second challenge. The third challenge, which is most difficult, how do I construct stack frame? Remember, when you call a function, you don't just send this parameter to that function. You don't do that. You construct the stack frame, right? And you put the argument in the stack in the right position, and then you jump to that function, right? And inside the function, they use EBP plus something to get that argument. That's how that works. Okay, you don't just put something and pass that to the function. So this is the third one. So if you just call something, okay, in your code, you call a function, okay, and that is not so difficult to construct the stack frame, but we are actually using the return address to jump to a function, okay, and that turns out to be more difficult, okay, and we will talk about that. So let's look at these two easy one, and then we get the third one. The finding the address of system, okay, and so this is actually very simple. You just actually go run your program in a GDB, okay. So you can see I'm setting actually the breakpoint, and then after that, and I just print out the system function, okay. Just P and system, whatever the function you want to call, you want to find the address. So and I get this one. And if you want to know the exit is another actual function in the libc, and you just print out exit, and it's going to give you the address. Okay, and that's very easy. You just go to a GDB, okay, and you don't need to even need to debug the vulnerable program, any program, okay, and because they all use the same shared library, and that address is always in the same place, okay, assuming we actually turn off the randomization. Okay, so that's very easy. Just GDB, and you should be able to find that function. Okay, now finding the address of /bin shell. Okay, so now I want you to think about how to do that. /bin shell, we need a string. We need that string in the memory. We also need to know that address. So how do I do that? Okay, there are actually multiple solutions to do that. Okay, how? So tell me your ideas.
Can we pass it as payload?
What do you mean passing the payload?
If like here our program is reading from bad file.
Yeah.
So if I include /bin/sh text in it. Then
Okay, very good. So because you actually overflow the buffer, right? So in that actually basically the array that you construct, and you can have the /bin shell, right? So except one problem. What is the problem? You can do that, but that's definitely the one challenge you're facing. So he's saying just put this in that bad file, right? Okay. Now assuming we put the beginning of the bad file, right? So the buffer, this buffer. Okay, and so the beginning of the bad file is going to be here, right? What's going to be the problem? You all forgot about the problem? Can you say again? That's a 0 inside, right?
Yes.
If you do that, your payload contains 0, because that's a 0 at the end. Okay, so how do you solve that problem?
Replace the 0 by 0 when you write the bad file, and you can do that even if it wasn't the beginning of
but this 0 is going to be there, right? How do you?
When you construct the bed file, you can replace the 0 by no after you write the slash bench.
So he's saying let's replace the 0 at the end with something else, right? Right? Would that work? Then there will be something else. It's not going to be a /bin sh command. It's going to be the /bin /sh, whatever you put in there, and that's no such command, and your program is not going to work. You need that 0, okay? You need that 0, okay? How did we avoid the 0 in a shellcode approach? How do we avoid that? We dynamically generate 0, right? In our code, right? Now you don't have that leverage anymore. You cannot even run your own code, right? Because every code you put in that shellcode is not going to run anymore. So you don't have that actually help anymore. Okay?
What if I write /bin sh after the return address?
Okay? So he basically said we can put it at the end, right?
Yes.
And I was just trying to trick you, just put it in the beginning, right? And you can put that in the end, right? You can put it in the end, okay? So, but it's still that 0. Let's say when they do the string copy, right? String copy, does string copy 0? I think it's copy 0, right? Yeah. Then so you need that 0, okay? So string copy does copy the 0, so you're okay. Okay. So the end 0 you need to be in the memory. Otherwise, you don't have a legitimate actually command string. So put that at the end of your bed file. Put the 0 in there. And when they do string copy, they copy everything, including that 0. So that will solve that problem. Okay. So that's one approach. Okay. Place that in the bed file. Okay. But just make sure, and you don't put the beginning, don't put the middle. Okay. Put. So let's say we are not putting that in the bed file. Okay, where do we put it? Think environment variable. Very good. How do you place that in the environment variable? Can you say it again?
Export.
Export.
Yeah.
Okay. So where's the environment variable located? On the top of the stack, right? When you run a program, right? When you run a program, and before your main functions, actually the stack frame is even constructed, and on the top of this, there's a lot of this environment variable strings in there. So all you need to do is to create a environment variable string and put /bin /sh in one of the environment variable, okay? And then when you run the program, and that environment variable is going to be in somewhere in here, right? And that string is going to be in somewhere, and you just need to find it. Okay. So these are the two typical approach. Okay, and then of course there are many other approach. Okay, but so let's see we're going to use this approach. So this way we avoid to put that 0 problems and for the bed file. So let's see we just do this. Okay, I'm just creating an environment variable. Okay, called my shell equal to this. Okay, and then if you just type the environment variable, and you can see that that's going to be in the environment variable. Okay, and then we need to find the address. Okay, so now when I run any program, inside of this bash, right? Inside of this bash, okay, if I run any program, including the victim program, and then /bin shell is going to be in this top of my stack, okay, including that 0. Okay, it's still going to be in there, and my job is to find out the address. Okay, so I just write a very simple program. Okay, and I run this program. Okay, I run this program, and I just get a UMV, and I just print out that actually the memory. Okay, and so if you run this, and you're going to find out it just print out the address for you. Okay, and for this program. And you can find this address using different way, and this is just one way to do that. So I'm just writing my own program. I start that program in this shell, okay, and this position is always going to be the fix, right? it doesn't matter what program I run, okay? It doesn't matter what program I run in here, okay? And this /bin share is going to be in the exact same position, okay? As I said, we turn off randomization, okay? So, and that's how you can, I just need to get this environment variable. I just print out the address, and I get the address, okay? So this is actually quite an easy one, okay? So you get address. So one of the things we actually did, when we first designed this lab, and one of the things that actually bothered us, and it took us a long time to figure that out, is we actually accidentally changed the file name. So we get the address, and it worked. And then accidentally we changed the program's name. So the program's name, let's say initially is Return-to-libc. That's the victim program. We run this victim program. Okay, and later on, for some reason, we changed the file name and changed it to Return-to-libc. Okay, the length of the file changed, and suddenly it doesn't work anymore. Our bad file is the same. This is the victim file, victim program. Okay, so I think we just changed this to Return-to-libc 2. Okay, yes. The length is different, and we create a bad file based on the investigation. And if we run this, it worked. And we didn't do anything else. We just renamed this to a program called Return-to-libc 2, and it didn't work. Now, tell me what could be the problem. Took us a long time to figure that out.
Your environment actually has, like when you're running a program, your environment has in there the name of the binary.
Very good, very good.
And that'll change the output.
Very good, yeah. So if you were there, you will save us a lot of time. So it took us quite a while to figure that out. Okay, it is because this program name is also in the environment variable. Okay, one of the environment variable contains the file, the program name. If you change this program, you shift the position of the string.
What if the length of the name was the same?
Then it's okay. Yeah, it's okay. So magically, if you use the same length, magically just worked. Yeah, it doesn't matter. Initially, we thought that maybe this is magic of the name, but we just changed the name to something else. It worked. It just if you increase by 1, decrease by 1, by 2, it just didn't work. Okay, and eventually we figured that out. And if you print out the environment variable, so if you go to GDB, you print out the environment variable, you're going to find out, and this is where that string is. The my share equal to this, okay? And then towards the end, there's a string like this. This is our program name. Whatever the program that you're running, and it's also in the string is also in there. Okay. Now, if you change the length of this program, okay. So, and remember this is the high address. Okay. If you look at this is D5 and this is 6F, so this FD5. So this is on the top. So although we print out this way, but this actually is on the top, and this one actually goes to here. Okay. And we fill the stack from the top, right? So if you increase this by 1, and you're going to push this off by 1, okay? And so the address that you found out is going to be incorrect address. You have to reconstruct your bad file, okay? So, and the program thing is going to be just started with some middle of the command, okay? It's going to start with middle. It's going to report the program command cannot be found. And it gives you this weird string. Okay, it's part of your program, part of your string. Yeah, so it's called bin/ss cannot be found. Okay, so if you miscalculate this, okay, and your command may actually be pointed to the middle somewhere, and then the system is going to print out the error message. So it's going to say n/s command cannot be found. If you see the command like this, you know maybe you miscalculated a little bit. Yeah, you can move this, okay? So, and sometimes the pointer could be pointed to any other places, and it's going to just tell them this one cannot be found, okay? So that error message may give you some hint, and and where your address actually point to. Okay, but eventually, I mean, you will find it out. Okay, so if you change your file name and now you know, okay, what the problem may be. Okay. Okay, so now we get the harder part. Okay, now we need to construct the stack frame. Okay. So let me just add one slice here just to. So let me explain what the problem is. Okay. So we have a stack here. Now we know the address of the system function. Okay. So now we can point that to the system, okay, function. So in our bat file, we're going to construct this. Okay. Now, once you enter the system function, system function is going to use inside the system function. It's going to see the same stack, right? It's going to see the same stack. Okay. Now, system function is going to use EBP plus what to get this a string. EBP plus. Remember, EBP in a typical function. Okay, when you call a function, EBP point to here, right? And so EBP plus 8, right? So this is going to be actually the first argument. Right now we only have one argument, right? So this is going to be the argument. So EBP plus 4 plus 8. EBP plus 8 is going to be where the system function get the argument. Now the problem is we messed up the EBP. Right? We are jumping to this. Okay? Now EBP used to be point to here, right? Inside of this full function, that vulnerable function. Now, so this let's say this is the stack frame for the full. Now EBP is point to here. Now when we return and this jump the system, okay? Remember when you normally returns, right? When you normally returns and this, you're going to actually recover, you're going to actually do some cleanup the action, right? And so, but now this is not actually the typical jump to a function. When you jump the function, you call a function, call foo. When you call foo, you set up the EBP, you set up many things, okay? But now we are not calling foo, we're not calling system. We just jump to the system function. And call system and jump to system. These are two different actually the instruction. They do two different things. Okay? Although the end result is the same, they both jump to the system. But when you say call system, when you call a function, so what's going to happen? What is the main difference between jump to system versus call system? They both actually jump to the system, to this address. What's the main difference?
In the call for system, the return address and everything is saved.
Return address is saved.
On the stack.
It's on the stack. Okay. Return address is saved on the stack. Okay. Okay. So when the return address is saved on the stack, what's going to happen? What register is going to be affected? ESP register is going to be affected, right? When you push something to the return address, is going to be pushed into the stack. That's going to affect the ESP. When you jump, do you affect ESP? You're not affecting ESP. Okay. So calling the function and jump to function, the ESP value are different. Now we are jumping to that. The system function doesn't know you just jump to me. System function thought you just call, right? And you actually use the call to come to me. Okay? And they will anticipate your ESP value will be some value. Right? So these are two different things. So we have to, although we are jumping to the system, we need to actually emulate what the core is, okay, what the core system is doing. And also, when you call a system function, you also push something into your stack, right? You push your argument into stack, right? Now, when we just jump to the system, we don't have anything, right? In our main function, if in our main function we do the call, we don't just call system. We have to prepare the stack. And that's a typical function invocation. You prepare the stack, put your argument in the stack, and then you call the function. Okay? And call the function is equivalent to jump plus pushing the return address to the stack. Okay? So it's a jump, but actually it pushes the return address to there. Okay? So now when we actually override the return address, we are not doing this anymore, right? And we don't push the return address in the memory anymore. Okay? We actually don't care about return anymore, right? But we do care about the ESP value. Okay? So that means when you need to prepare everything before the jump. So you can see the call actually the push and the jump, right? The prepared stack also involve a few push. Now you only do the jump. So you got to do the push, but you cannot run the code, right? And so you have to construct your bed file. So your content of your actually the data is going to be on the stack before you jump. So you kind of have to manually construct the stack by yourself using the overflow. Okay? You cannot run any code. Your code is not going to run. You have to use other people's code. Okay? So that actually makes it more challenging to really to find out where do I put that argument. Should I put in here, put in here, put in here? Okay? And in order to know that, you need to know where your EBP is. That's very important. Because EBP plus 8 is where you're going to put that command. You already know this the address for that, /bin sh. You know the address, but where do I put this address? And you need to know once I'm enter the system function, the most important thing is what is my EBP value. Okay, if I know EBP point to here, and then I know, okay, I just count 8, I'm going to put this address into here. Okay, so that is easy. But where's my EBP? That's what we're going to figure out. Okay, in order to really understand where the EBP is, and you need to understand actually the assembly code. Now let's look at the assembly code. You can compile your code into assembly and using the -s, the capital S flag, and you can look into your actually the assembly. Okay, and I removed a lot of other code. Okay, so the whole assembly is kind of messy. There's many other things, but I removed them. Just look at some of the code which are relevant to us. Okay, so in the main function we are calling the foo. Okay, so this code is main function calling the foo, and in the assembly you're going to see that actually it's called foo. Before that, it actually you can see it operates on the ESP. Basically, push something the argument into the stack. Okay, now once it's into call the foo, there's always these two parts which are standard for all the function. Okay, this is irrelevant to the first two lines, not the first two lines. Okay, and these two lines. And this is independent of the logic of your program. And this set up EBP, set up ESP. Okay, so let's look at what they do. Okay, so now we are in the main function. Okay, so let me just draw the stack. In your lab report, you need to basically draw the stack like what I'm doing, and then show the TA, and that's how you calculate that position. Okay, I want you to be able to do that yourself. Okay, instead of just say here that is a position. Okay, I will want to say the stack. Okay, and you can draw that, and you don't need to actually use the computer program to draw. Take a piece of paper, draw that on the paper, then you all have some smartphone, right? Take a picture of that and just upload it or scan that. Okay, and I don't want to spend too much time to draw the beautiful picture and using PowerPoint or whatever. Yeah, just handle return is fine. Okay. So here's the main. Okay, this is the main frame. Okay, the stack frame. Now it's going to push some of the data in here. Okay, to start the foo. Okay, so now let's see some of the information is going to be put in here, the argument. Okay, now it's called foo. Okay, as I said, when you call foo, it involves two actions. The first action is there's an EIP register which point to the next instruction. Okay, so the next instruction is here, is this one. So basically that instructions is the edges of that instruction is going to be pushed into the stack. That's our return address. So this call basically actually take the EIP, the value, okay, and of course the EIP value for the next instruction, and save that into here. That becomes the return address. It does a push, okay. So this involves a push and jump. And that's how your return address is actually pushed into the stack. Okay, and there's just no magic. Okay, and this is everything is actually in that instruction. Yeah, return address is in here. Okay, and then you jump. Now, when you push the ESP value, which is the register to point to the top of the stack, it's going to move. Okay, now ESP is going to be here. ESP. We need to trace the ESP. Because ESP decides the value of EBP. That's the whole point of tracing the ESP. So ESP is on point here. Now we are in the foo. And it's going to jump to the foo. Get to here. Now if you look at the first instruction, what does first instruction do? Push EBP. What does push EBP means? EBP right now is point to the stack frame of the main function. What does push EBP mean?
Put the address into stack.
What is the meaning of that?
Save the state.
Save the old EBP, right? This field is old EBP. This old EBP value is going to be here, right? Because EBP need to be remembered here. So this field is old EBP. That's what this does. As I said, there's no magic. And saving this old EBP is actually in the code. Okay, in the compiled code. Next one, what does next do? Move ESP to EBP. Assign this value to here. What does that mean? Assign ESP. Once you actually you push this, your ESP value is going to change. Okay, you always have to trace the ESP. Okay, the critical part is to know where exactly ESP is. Now ESP point to here. Next one, move ESP to EBP. What does that do? What is the meaning of that?
EBP points to that.
That is basically updated EBP, right? So EBP used to be here. Now it's going to be updated. Okay, EBP point to here. That's what we know, right? EBP always point to this place for the current frame. That's how the EBP is set up. That's how the old EBP is saved. That's how the return address is saved. Okay, and so all the function will do that. Okay, so this call plus this three instruction basically they construct this return address, old EBP, and EBP. Okay, and after that, so this one I shouldn't use a bold for the font. This one is specific to this function, and it's subtracted at ESP by 24. And what does that mean? So ESP is going to move to here, ESP, this 24 here. That's to allocate the memory for the local variable. Because this local variable requires 24 bytes. So it actually push ESP. So because this one is going to be used by local variable. And that 24 is really depending on your local variable. Okay, if you don't have local variable and you don't have this instruction. So we don't need to worry about this. Okay. So ESP, during the execution, ESP can change. Okay, because the program may actually use a stack. So ESP can change. Okay. Now, after everything is done, okay, we don't need to worry about what goes inside. Okay, after everything is done, and if you look at the assembly code, and it's going to call the leave and the return. The leave actually does two things. This is what the leave means, instruction. Does two things. Let's see what that means. Okay, move EBP to ESP. Move EBP value to ESP. What does that do? So right now, at this point, ESP point to here. And move it back, right? so basically says, oh, okay, I'm done, and I don't care where your ESP is, because everything here is going to be freed, right? Because that's a local stack. So actually, the ESP moved back to here. Okay. So everything here is going to become the free memory. Pop EBP. What does pop EBP mean? Pop EBP means going to take the whatever is on the top of the stack and assign that to the EBP. What does that mean? It let EBP point back. Now EBP point back here. Okay, now it's reconstructed. So EBP now point to the main function. Okay, now we are ready to return. Okay, so we got our old EBP back, right? We got the ESP point to here, right? Now the next one is the return. What does return do?
It pops now the return address and puts that into the.
Okay, so yeah, great. Let me. I forgot one thing. So pop EBP. After you pop EBP, where's your ESP value? Okay, ESP now point to here. Now return basically is going to be pop whatever's pointed by the ESP. Okay, which happen to be the return address. Right? So it will pop that and jump. So return basically dot pop and jump. And it's a reverse of the call. Calls push and jump, and returns pop and jump. Okay? So that's how this return address is saved, and that's how the return address is used. Okay? As I said, there's no magic here. Okay? Everything is in that instruction. So that's exactly how it works. So ESP has to point to here, okay, and then this return actually instruction basically pop whatever is in here, and then jump. After that, your ESP going to point to here, right? So that's where your ESP is. That's what you need to remember. Okay, when a function returns, ESP is going to be point to here. Okay, and it's going to be point above your return address. Okay, and this is actually the normal function call. Okay, and if you have a main function, you call foo. Okay, and then when you return, okay, and ESP now is going to move to here. Okay, and then in the main function, and it will actually do the utility in its own way. So, but we don't need to worry about that because at this point. In our buffer flow, at this point, we're going to actually jump to the system function, right? This return is not going to jump back to the main function. This one is going to jump to the return address, not to the actually the system. Okay, so now if you understand this, now what I'm going to do, I'm going to ask you to do is, I'm going to ask you to calculate that. Okay, so I'm going to give you, let's see. We got 40 minutes, about 40 minutes. I'm going to give you 10 minutes. Okay, so this is how it works. Now in this attack, this one now is going to be overflow, right? Now we're going to have overflow with this one is going to be jumped to the system now, right? And when you return, okay, and ESP is still going to point here, and EBP is going to be. EBP probably is not going to point to here anymore because you already modified this value. So EBP is going to point somewhere, right? Because EBP is going to be actually the point back to this value, but you have already overflowed this two part. So the EBP's value is going to be some random value you put in here. Okay, so it doesn't point back to that. This one is going to be system. Okay, so this used to be the return address. This is old EBP. and ESP now is pointing to here. Okay, now you jump to the system function. Your system function, the beginning 2 is going to be exactly this 2, okay? The third one is going to be different. But the first 2 instructions is going to be this 2 instruction. Okay, now I want you to tell me where do you put the address for the /bin/shell. It's going to be somewhere on here, but exactly which location? Okay, I want you to find out. Okay, so you do know the ESP, as I said, this critical part. You know the ESP. Now it's going to be pointed here. Okay, and when you jump to here, when you jump to the system, now you are into the system. Okay. Now, remember you also have to. The first 2 instructions going to run these 2 instructions. Okay. And then after that, okay, you're going to get your EBP value. Okay. And from there, and once you get your EBP value, okay, and you should know where that address EBP plus 8, right? So the idea is you trace ESP. From ESP you find out your EBP. From EBP you find out the location for the argument. And so basically you need to pinpoint where the EBP points to once you enter the system function. So now imagine this will be the system now. Okay, it doesn't matter what functions, they all have the same thing at the beginning, they all have the same thing at the end. These 2 instructions are the same for all the functions. These 2 instructions are the same for all functions. Okay, so I will let you to spend 10 minutes to figure that out. Okay, and if you already figured out, let me know. Okay. Just focus on these 2 instructions. Okay, so now once in the full function, once we return, okay, we basically jump to these two instructions in the system function. You just need to know how these 2 instructions change the ESP, change the EBP. Okay, you basically just have to mentally actually execute this command, these 2 instructions. And then by doing that, and you can pinpoint where the ESP value is, no, EBP value is. Okay, and EBP plus 8 will then be the actual argument. Okay, so let's look at this. Okay, I know although once I show you that and you will understand, but it's really deriving that is not that easy. Okay, but I hope that you can practice a little bit. Okay, it involves some actually the assembly code, but these codes are very easy to understand. Okay, and this is the skill that I want you to have. Okay, remember when you study security, the hacking is a very important part of that. This is the hacking part. Okay, so you should be able to know exactly how to calculate that address. Okay, so let's look at this. So now let me just remove this. So this is the return address, which is now pointing to the system. Okay, and so the full function now is going to jump to the system. Once you jump to the system, okay, and before that the EBP now contains some value which you put in here. Okay, which we don't know what that value is. Okay, and of course you know it's in the bad file, but we don't care about that. Now, once you jump into this, we're going to start in the system. Let me just rewrite the system function. Okay, I only write this first 2. So when you jump, okay, as I said, ESP now point to here now, because this is going to be freed. Okay, we are going to jump to here. Now let's look at what the first instruction does. Once you enter the system function, the first instruction is to push EBP. What is EBP value? Somewhere, okay. So somewhere is going to be pushed into here, right? So the EBP, this value, let's call this value is X, okay, somewhere X. Now X is going to be pushed in here. Okay, we don't care about that value. Okay, and that value initially was pointing to system. Now it's going to be different now. Okay. And now, but the result of that is going to move the ESP pointer, right? ESP now is going to move. It's going to move to here. Okay, so that is more important than the actual value here. Now the next one is going to move ESP to EBP. ESP is not here, right? So now it's going to actually move the ESP to EBP. That's going to be like the EBP point here, right? So that's why we don't care about that value, okay? Because the EBP is going to be reconstructed, okay? So now EBP is going to push, it's going to move to here, and both ESP and EBP move to here, and that's what we want to know. At this point, EBP is going to point to the system function. EBP is pointing to the old EBP, right? To the system function. But actually, that's not the case. What is important to know is that inside of system, EBP plus 8 is how the system function get that actual string. Now you can calculate EBP plus 8. It's going to be here. That's going to be actually the string, the address. Okay, that's you put the address here. You can see your EBP actually point exactly to the older return address now, right? That's older return at that position, which used to be hold the older return address. Now it's to the system function, this hold the older EBP. Okay, so but actually it's a random number put in there, and so plus 8 is going to be here. Okay, so you can see the calculation is very simple. Plus 8 of the original return address. Okay, that's why once you know the answer, you can construct your bad file right easily, right? But as I said in your report, I want you to calculate y plus 8, right? Y is 8. It is 8 above the old return address, and you need to be able to show the stats. Okay. Now, there's one more thing, and you need to think about right now is once now we are enter the system function, the system is going to finish, right? And at the end of the system function is going to return. Right? Where does it return to? Where is it going to return to? It's return to whatever you put in here, right? Because EBP is going to point here. This is going to be the new return address to the system function. What do we put in there? Maybe just a random number, right? Maybe just a random number. So, and when the system function returns, it's going to be returned to that random place. And the program will crash, most likely. Right? What if you don't want the program to crash? You want it to nicely exit. And to do that, you want it to return to another function called the exit function. Exit function basically do the cleanup, and then the nicely just exit. Okay? So that's function called exit. Okay? So now if you want it to return to the exit, what you need to do is you need to actually find the exit address and put that address in here. So that's actually the return address for the system function. So when the system function returns, actually jump to another function. Okay? And that function happens to be the exit, and that will just exit nicely. Okay? So you won't crash your program. Okay? So in the lab, we like you to do that. Okay? So you need to first, of course, get it to work, and then just actually put the exit, and just very, very simple add-on to that. Okay? So you don't need to have a shellcode anymore. Okay? You don't need to worry about the zero. Okay? And all you need to do is actually to find the address, and hopefully the address of the system function doesn't contain 0. Okay? If it contains 0, that's going to be trouble. Okay? And at least when I try, there's no 0 in there. Okay? So if there's a 0, and I'm sure there are ways to solve that problem, but we shouldn't have that problem. Okay, in the lab. Okay? So is it clear? Okay, so it's definitely more complicated than the shellcode. Okay, shellcode is very easy. For here, you need to be able to calculate that.